So our first speaker is Eric Peterson, who's the director for WebCore Concrete in San Francisco, California, and has been on the WebCore team since 2000. His career has included projects within the heavy civil, transportation, building, healthcare, and industrial sectors. He has over 45 years of experience in the construction industry with base crafts of carpentry and welding. He is an active member of ACI Committees 117, 237, 301, 321, and 347, and also ASTM C09. I would like you to welcome Eric.
So as Amon, thank you, Amon, pointed out, my background is in the trades. I started as a carpenter helper. My first production carpentry job, $2 an hour, working in Harvey, Louisiana. And I grew to like concrete very much, partly because I liked the material and I liked what you could build with it, and also because the jobs lasted longer. So to advance, go here. I'm going to make a presentation on the present vertical tolerances that ACI publishes. And I want to point out that many project specifications are specifying something other than what ACI publishes. I'm going to explain why. We're going to look at what our tolerances are, what they mean when you're building a tall structure, and kind of offer some thoughts on where we might go with the tolerances that we have. Also, I'm going to discuss by comparison, and also because we live within their world as well, the tolerances by AISC, the American Institute of Steel Construction, and the National Elevator Institute Incorporated. And I'm also going to briefly talk about how we measure tolerances to see if there might be another way we both represent them in the tolerance standard, because very few of us are using plumb bobs anymore to bring up control in a building. And honestly, I remember when I first started that it wasn't uncommon to have a very heavy plumb bob hanging down in the elevator shaft, and that just doesn't happen with total stations and everything else we're using now. Make sure I didn't skip one. So the way the ACI tolerances work is that from the base of the element, you measure the location relative to the northings and eastings control of the project. And right now, that's the only place you ever measure it. From there, you plumb up from that. You're still referencing building line, but plumbness is gauged by is the only place that it says in the specification to measure the horizontal location of a vertical element is at its base. And in the first 83 feet 4 inches, we have a maximum slope out of plumb of up to 0.3%, okay, or approximately 3/8 of an inch and 10 feet. At 83 feet 4 inches, the maximum we can be out of plumb is 1 inch. And that you can get to 1 inch using a 3/8 and 10 slope in 27 feet 9 1/4 inches. And then for above 83 feet 4 inches, the maximum slope drops down by 3 times to 1/8 and 10, or 0.1%. And then you progress on an envelope that if you multiply that slope out for the next, whatever the difference is between 583 foot 4 inches, you end up with a maximum gap or maximum out of plumbness of 6 inches. The important thing to always remember with ACI tolerances, and it says it right up in the beginning of chapter 1, is that they're not cumulative. So what this says here on the bottom, if the base of the wall is incorrectly located by the maximum amount allowed in section 4.21, which is 1 inch, then the plumb tolerance dictates that the face of the wall move back towards the correct location, okay? So you don't get to put anything together. These envelopes that we're describing, the envelope that you see right there, that's all you get, all right? AISC has a little bit different tolerance structure. They have an allowance for 1/4 of an inch at the base maximum, but they also have a caveat that they don't really control the base. The anchor rods are put in by somebody else. Wherever that base is, that's where it's going to be. But they do attempt to make the best fit for the structure when they set. There's always tolerances and bolt holes, and they attempt to make a best fit, but that's their tolerance at the base. They have one slope and one slope only, and that's 1 in 500. That goes all the way up the building. And they have a couple of thresholds where you can, they have to remain within 2 inches inside and 1 inch leaning towards the outside. So they have an asymmetric envelope. You have more tolerance going in than you have going out, okay? And then once you get up to level 36, you can be as much as 3 inches towards the inside and 2 inches towards the outside, and then that's all you get, okay? The elevator, NEII, their tolerance is easy to state, up to 100 feet. The sides of the elevator shaft can only encroach 1 inch. From there onwards, you get a 32nd of an inch in 10 feet to continue to migrate outward up to a maximum of 2 inches. 1 inch is the golden rule inside an elevator shaft. So we can already start to see how much we're deviating, how much difference there is between these various tolerances that are being used in structures, tall structures. So what you're looking at now is a tolerance from a project specification. It's a little bit different than AISC in that it's symmetric, and it prescribes a very definite location of where you can transition from a 1 inch max and start migrating towards a 2 inch max. It has the same constant slope of 1 in 500 or 1/4 of an inch in 10 feet. And the maximum deviation at the very top is 2 inches, either inside or outside. The same specification provides basically the same requirements for the elevator shaft that I just described, of being allowed to encroach 1 inch on either side, up to a maximum of 2 inches of total encroachment. And then the 1/32nd is kind of almost doesn't matter, because you're basically limited, mostly constrained by the 1 inch that you're allowed to encroach on either side. So using this tolerance system, I want to just talk a little bit about what it means. This is an elevator shaft located on the 38th level of a building we built. The shaft is affecting, if the core wall is out, whatever amount it is potentially impacting, it's affecting the toilet. This is a code clearance requirement. Now you can see they've provided some furring there. There's a little bit of adjustment, okay? And it affects this pocket for the door in the lobby, in the fire lobby. And also it can affect this location of this vestibule wall. And a vestibule has to maintain a definite dimension, right? You can't, that is a minimum. The room in that vestibule is a minimum. It also affects this corridor. If the core is leaning in one way or another, it'll affect the minimum width of this corridor. So the designers are bound by code minimums in many cases, and it's not uncommon to see this many things around a core. In fact, seeing bathrooms next to a core, both in residential and commercial structures, is very common. The thing is that when we lay out sleeves and things like that, that's all done with a total station now, and the mechanical and electrical contractors come out there, they clamp the total station onto a column, and they lay out every sleeve in that building. And they're referencing control, right? They're not referencing walls. They're not going to do that, and that's not really a good way to build. So we want to have the ability to accommodate tolerances in the sleeves they put in the furring around these walls. The tolerances that exist must be accommodated. So next slide here. This is the red line going around this same core, only this is up at level 40, represents, and let me back up just one slide here. Right now we're 473 feet above the ground level. So we're very close to the maximum of what ACI would allow of 6 inches. So if we had the 6-inch tolerance, that red line around this core is what the designers would have to provide in order to, you know, accommodate a core moving as much as 6 inches at that elevation. And it's quite significant. You can see that it makes a big difference in terms of what kind of accommodations you have to supply for like that toilet room and everything else. It's not an easy thing to do. It also, a big deal for the owners is that it affects the marketable amount of real estate. When they go and do their calculation of what real estate they have, they're losing area. And as trivial as that might sound, because it's just this ribbon around the core, it adds up in a tall structure. It's not insignificant. I figured it out. I mean, it ends up being a sizable space, you know, like maybe the space we're sitting in here, right here, by the time you get to the top of the building. This is another standard that was in a specification, and this is one we were fortunately able to negotiate. This one had a 3/8 and 10 with a maximum in 20 feet of 3/4 of an inch, and then from 83 foot 4 inches and more. In other words, all the way to the top, they wanted us to stay within 1 inch. And I don't know how many people here that build would be happy about signing a contract with that kind of tolerance in it, but that's what they require. We didn't. We went through the drawings. We discussed this with the engineer in our pre-job meetings. Even though they had that 1 inch tolerance, we were able to find a number of locations where they hadn't accommodated the tolerance. So I'd just like to make that a kind of a lesson there. You need to look and make sure that even though the structure you're building has tolerances, you want to know that the architectural details actually accommodate those tolerances. How are they going to adjust for them? Right here, for example, that column is next to a kitchen that has overhead cabinets. I mean, they don't have any room there. There just isn't any room. And same thing with their toilets and things like that. So what we basically got to them to was more or less a tolerance which was similar to the one that I just showed you of the 2-inch maximum, with like one exception. We could only figure out how to get 1/5/8 tolerance with the architectural details that they had to accommodate. So this is what, you know, a typical core wall looks like in California, and I imagine a number of other places. There's a lot of rebar on these walls, and in many cases they're only designed for 3/4 inch cover. So it takes a lot of effort to keep something like this aligned. What you see up here, that tube steel there, is the beginning of what we call a halo that we use to keep the core wall kind of contained within its maximum out-to-out dimensions, and then we keep that plumbed as we go up the building. But going through, this wall isn't ready to close up yet. This is kind of just fairly soon after it was erected. But we have to go through and really make sure that we're keeping this tight, because the rebar can dictate where you have to place the concrete. So if you're not controlling the rebar, you're not controlling the surfaces of your concrete. So there they're putting in a coupling beam. In this case, they're using a structural steel coupling beam. And again, it takes, like I said, it takes craftsmanship and experienced oversight. You just can't sit back and think that this is going to happen by itself. This is the same building, and we, you know, because of the tolerances, they're surveying these buildings. I mean, if we're responsible for something, if steel has to be modified, if architectural details have to be modified, they're coming back to the contractor. And, you know, that's just the way it is, right? So they measured this building all the way up. Our maximum deviation on this building was 1 5/8". I don't remember exactly which level it occurred, but on this level here, you can see that our maximum at level 46 was 1.25". So the reasons we're trying to maintain these tolerances are, one, of course, I just mentioned the marketable area, the fit up of adjoining elements, accommodating less deviation, simpler than connections with accommodating smaller deviations is simpler than accommodating large deviations. Yeah. So my question in this presentation is, what's right? Can an ACI, should we just keep going with this tolerance envelope on vertical elements? Because what happens is that very few of the designers like it on tall structures, and they almost inevitably will specify something more stringent. If we specify our own tolerances that are based more on consensus, then we can defend them. For example, if we wanted to say we want 3 inches both ways, and if we have other people working with us, people from the NEII, people from AISC, and other people who are affected by this, window wall people, things like that, if they're saying that they can accommodate, a tolerance, we decide that 3 inches are a number. Hitting 2 inches is not easy on a tall structure. And I think that they build similar structures to us, and I think he'll nod his head saying that doesn't happen by itself. It's very difficult. It's very difficult to be contractually tied to. So the reason I'm giving this is I think that we should reconsider our tolerances so that we have this within our control and not get told on every job what our vertical envelope is. I would like to have some control over what it is we can do and then be able to represent that with some consensus for people within our industry at large. This is just what I wanted to talk about in terms of how we measure tolerances. This is a pre-pour scan that I did. I'm looking at the rebar cage. Again, if you don't control the rebar, you don't control the surface of the concrete. I'm noticing that this column is eccentric. It's got an 1.16" clearance at the top from its model location, and 4 to 8 inches there. When they lap that column, the rebar cage that goes around it, it's not going to be inside the column surface. So that's something we fix before we pour. But what I want to point out here is that we don't bring a plumb bob up to measure that. We're measuring it off of control lines. Yes, we bring the control lines up vertically, but after that, we're still measuring location relative to grid coordinates. So my question is right now, as I stated before, we're only evaluating the tolerance at the base level, the bottom support. But in fact, in practice, we evaluate it according to X and Y all the way up the building. We're always doing that. So I'm saying that maybe we can state our tolerance in our specification a little bit different. We could state the tolerances on vertical elements to be provided by stating a maximum slope, independent of height, above the ground level, and a maximum horizontal displacement as a function of height. Just a different way of writing it and a different way of putting it, of phrasing it, because we in fact measure them that way. We don't measure them using a plumb bob. So this is my concluding slide. As it exists now, designers are specifying tolerances more restrictive than ACI 117 specifies for plumbness on tall structures. Building architectural layouts are not assuming the ACI tolerances. You look at what they've designed, where they're allowing clearances, there's no way they're accommodating 6 inches of movement on tall structures. It would be very difficult for them to do. It becomes very difficult if you have a core wall that's supporting structural steel and it's extending out to the curtain wall, and they have to make that much of an adjustment in their clip connection, their shear tabs out of the exterior columns. That creates a lot of additional stresses. I mean, it's structurally difficult to have a larger connection that they have to make. There's an inconsistency between AISC and ACI plumbness. Our tolerance structures are not the same at all. They are inevitably going to clash. There's no way that those two tolerance systems work together because they don't have the same slopes, they don't have the same values. We are fundamentally set up to have a conflict with the steel.
You're great.
Okay. We're also not consistent with the tolerances for the elevator shaft, and honestly, the elevator shaft is the hardest to control. And that's something where we should probably have some elevator people on our committee and start figuring out, and some architects and engineers, because that's really something where we can have difficulty. If we can hit the 2-inch tolerance, that's great, but you can see that we're already exceeding the 1 inch on the floor. But I think we did okay on that shaft. And a lot of the times I find that there is more room. If you start to talk to the elevator people earlier in the job, you'll find out they've got a little bit more than that 1 inch. They can almost live with the 2 inches that we're doing input for the, you know, for the entire structure. But you got to have that discussion. You got to know where you stand, and they got to know what you're going to try to get done. So owners are concerned with the area. I don't know. I guess that's an issue, but it is their concern. And then I'm saying, should ACI 117 reconsider the plumbous tolerances being used to develop consensus among designers and building system installers, or continue publishing the tolerances we have? And you know, there's this thought that, you know, maybe you know, we're starting to constrain ourselves by publishing a tighter tolerance system, but I'm thinking that we're getting constrained anyway, and I would like to have some control over that constraint. So that's the reason for this presentation. This actually was going to be given a couple of years ago before COVID, and it's an outcome from a presentation I actually gave at a 117 meeting that they thought that I should share with a larger audience. So with that, thank you.